So we're looking at elementary statistics, chapter 11. We'll be doing section 11.2, but kind of leading up into what's going on here. Chapter 11 talks about the goodness of fit and then contingency tables. So we start comparing and trying to figure out whether we have some comparison between two things with multiple examples. So they give kind of a little chapter problem here where they talk about that if we were to give a child $1, or we give them 4 quarters. So we're given the same amount of money. And then we put them in front of a gumball machine. We start figuring out, well, are they going to purchase the gum or are they going to keep the money, once again, based off of here. So we start seeing, is there a relationship between what we give here and what they do over here? Or is there not any relationship? So that's what this section and this chapter is starting to relate to. So we're looking at the goodness of fit test. The goodness of fit is used to test the hypothesis that an observed frequency distribution fits some claimed distribution. So basically we're trying to figure out, is there some sort of proportional results that are relating to each other? So the objective here, we're going to conduct a goodness of fit test. Once again, this is a hypothesis test to determine whether a single row or column of frequency counts agree with a specific distribution or uniform or normal. Okay, so we will have a couple things. We'll have an observed frequency of an outcome. We'll have an expected frequency of outcome. We'll have the number of different categories and then the number of trials. So once again, the requirements. The data have to be randomly selected. Okay. The sample data consists of frequency counts from each different categories. For each category, the expected frequency is at least 5. Okay, so we want to be at least 5. Our null hypothesis and alternative hypothesis. So the null hypothesis counts agree with the claimed distribution. The frequency counts do not agree with the claimed distribution. Okay, so this is kind of how these frequencies go. Basically, the null is what were claimed, and then the alternative is what is not claimed. Okay, and then what we're going to have to do is we're going to have to calculate out this value right here. So we're going to take the summation of our observed minus expected squareds divided by the expected squared. So we're going to have to be very detailed with our work in here. And then once again, this is a chi-squared test. So critical values are from our table A4. Once again, K minus 1 for degrees of freedom. The goodness of fit tests are always right-tailed, which is what chi-squared tells us. Okay, so what do we have to look at here? We got to figure out what is the expected frequencies are equal. Okay, so if we talk about there's a 25% chance that any of these categories is going to happen. So we have 4 categories, 25% chance for each of them to happen. Basically, we're going to take the number divided by k is going to give us that E value. Okay, when we talk about expected frequencies are not equal, so we're saying that there is a 50% chance you'll get an A, a 25% chance you'll get a B, a 10% chance you'll get a D, so on and so forth within our different categories that we have, or within here on the comparison of what's going on, we would have different availabilities on here, so there's some sort of difference in probability. This is where we would take the n times the probability then, okay? So the number of trials times that relationship that's going on here. Also note, I have this little bit right here, also note that the observed frequencies are all whole numbers because they represent actual counts, but the expected frequencies need not be whole numbers. So for instance, whatever we're talking about, we could relate flipping a coin and generating the probability of a head would be 0.5. So if we had 10 trials, we'd see it 5 times. But technically, we could have 5.5 heads in 10 trials. That's what this is being related to, that the expected does not have to be a whole number. It's going to be relating to whatever probability we're relating with, and the decimal values on it. Continuing on here, they have this graph on top here, kind of giving us a little flow chart. We talk about, we're going to compare the observed values to the corresponding expected values. Once again, are the observed and expected values are close, or are they far apart? Okay, if everything is close in here, we will fail to reject. If they're far apart, we will reject the null hypothesis. Thus, if we fail to reject the null hypothesis, the good fit was assumed distribution. The not good fit was, or not a good fit was assumed distribution. Okay, so that's kind of where we're going at with this. Once again, they have some statements in here. Please remember, a lot of our stuff we'll have our test statistic, but we also have a p-value. Remember that p-value related to our significant level that we're testing towards. So if the p-value is low, the null must go. Okay, so basically it's just a little statement that if our p-value is less than what our significance level is, then our null, we must reject that null hypothesis because it's just not working within. So the calculator format. If you look right here, we have a chi-squared Gof test. Okay, we will have to enter an observed list and then an expected list, and then it'll ask for the degrees of freedom within our category as we go through and we enter in this data. So we'll have to enter into spreadsheets, our lists, we'll title our lists, then we'll have to bring them in under this testing format. Kind of looking further ahead here, that's about all that is in this section. Once again, I'm going to be showing you how we're going to use the calculator for this. Main things are going to be stating those answers and concluding what is going on. Once again, this is dealing with comparison within a table. Okay, so we're comparing kind of like a frequency right here. We'll have a list of digits and we'll be talking about a frequency within there. Once again, this could be an equal frequency or it could not be an equal frequency is what this relates to.